All right, kids, let's talk thermochemical equations, the craziest thing you're going to learn in this unit, the most difficult topic you're going to learn in this unit. LOL, JK. You actually already know how to do thermochemical equations, which is crazy because you already know how to write chemical equations. The only thing we're adding onto it here is thermo. So what we're adding in is talking about heats of reaction now. What you learned is delta H, right? Your change in enthalpy, your heat of reaction. It's just simply telling you, is your reaction exo or endothermic? Is more energy released or absorbed in this chemical process? So we're going to do a little example to talk about potential energy diagrams first, since this is a little review of the last topic that we looked at. So let's think about this example equation here. You have hydrogen peroxide, H2O2, and it's decomposing into oxygen and water. So first, think about what type of reaction this is. I kind of already gave it away. Decomposition. Okay, so this is decomp. You have one reactant breaking down into multiple products. So let's say you had 27.8 milliliters of your hydrogen peroxide and all of it reacted. What we are asked to figure out is how many grams of oxygen gas will be produced. Reason why we're starting here is because we need to do a little stoic review for us to be able to do stuff with thermochemical equations. So we're also given the density of hydrogen peroxide. We're told 1 gram is equal to 1 milliliter. So I'm going to start with my 27.8 milliliters of H2O2 because this is my known. At the end of this, I want to end up with grams of oxygen gas. So the first thing I got to do is get this into grams. I'm told that 1 milliliter of H2O2 is 1 gram of H2O2. Now I can work with my normal units that I'm used to, right? So how am I able to convert between grams of one substance to grams of another? Well, I have to go through my little mole map and think about getting to moles first, because moles is my only comparable unit. So I'm going to start with getting from grams of H2O2 to moles of H2O2. Then I have to compare my two substances that I'm converting between. So I've got my H2O2 and my O2. Think about the mole ratio, how these things are going to react in a chemical equation. For every 2 moles of hydrogen peroxide I react, I'm going to make 1 mole of oxygen. And my last step, how many grams of oxygen am I going to make? Well, I use my molar mass conversion factor for that. So I'm going to leave my molar mass values out. I'm going to let you fill those in and get your final answer here, but this is how we set it up. Okay, so the next thing we have to think about just after our review of stoic is now heat of reaction. So we are told that the heat of reaction, or delta H, for this reaction is negative 191.2 kilojoules per mole. So stop and think, what does that mean to us? Is this reaction exo or endothermic? What does that negative tell you? Well, the negative tells you that there's more energy that's released in this process. So if more energy is released, we should know that as an exothermic reaction. What does this mean about the energy that's involved in this? In every single chemical reaction, you have energy that is absorbed and released. You can't have one without the other, right? In order to break our atoms apart from each other, to break those chemical bonds, you have to put energy into the system. So energy must be absorbed by your reactants. Then, when you rearrange your atoms, you put them back together and you form new product bonds, that process releases energy. So when we're talking exo or endothermic, it's really, is more energy absorbed or is more energy released in this process? So for us, this is an exothermic reaction. Sorry, I didn't leave you any space, I forgot. So what does this mean about the energy involved here? It means more energy is released when product bonds form. Or you could say less energy is absorbed when reactant bonds break. So if we think about a potential energy diagram for this, we learned how to draw potential energy diagrams in our last lesson. So if we think about our axis, our X is going to be reaction progress, what happens to the reaction over time, and then potential energy gets tracked on the Y. So stop and think, which graph does this look most like based off of the ones that you just did? Well, more energy is being released here, which means we're resulting in a net decrease in the H of the enthalpy of our products. So our reactants are going to start higher in energy. Our products are going to end lower in potential energy. And then we have to put that little curve in the middle to get through the reaction. Remember here, this value is our delta H. This is our change in enthalpy or change in heat energy between our reactants and our products. And since this is exothermic, it's a net release of energy. The reason why this is curved is because we have to have our particles collide with a certain amount of energy to make the chemical reaction happen. That's why we don't have chemical reactions like just consistently going off all around us all the time. You don't hear little pops and bangs and booms just as you're sitting around the room. There has to be some activation energy that goes into it. There are chemical reactions that are happening, by the way. I don't want to make it seem like there's never a reaction happening around you. But I mean, your particles have to come in, they have to hit each other with a certain amount of energy in order to make any reaction happen, and that we call our activation energy, abbreviated E sub A. And then our reactants start over here, products end over there. Okay, so this is a quick little review of potential energy diagrams. Now we're going to talk thermochemical equations. Okay, so this is an example of a thermochemical equation that you see right here. A thermochemical equation is a chemical equation that has thermochemical data in it. So the chemical equation part is this. The thermo part is this, the change in enthalpy that we're given for this reaction. So stop and think, is this reaction exo or endothermic, and how do you know? It has to be exothermic because what we see is that our delta H is negative. This means more energy is being released here. So if we try to think through this in terms of like how we would speak, how we would read this chemical reaction, let's think about how many products and reactants we have and what's happening to their bonds. So we're starting out with 1 mole of PCl3. This is going to react with 1 mole of Cl2. When these things react with each other, what are we going to make? We're going to make 1 mole of PCl5. Okay, so now let's think about the thermochemistry part of it. When you break your reactant bonds, anytime you break reactant bonds, is energy absorbed or released? Energy is always, always, always absorbed. You have to put energy in first to break the atoms away from each other. Okay, now let's think about what happens when we're forming the product bonds and how this leads to an exothermic reaction. Because this is exo, is more energy released or absorbed? More energy is released. So if you think about it from breaking the reactant bond perspective, breaking the reactant bonds will absorb less energy than the energy we get out when our product bonds form. So if we carried out this reaction, what would happen to the temperature of the surrounding area? Well, if the reaction is resulting in a net release of energy, the surroundings will then absorb that energy, increasing their temperature. Okay, what I'd like you to do is pause the video, and you're going to try and recreate this sentence, this part B that we talked about here, and you're going to do it for this reaction in this box. Think about what is the thermochemical data that's represented here. Is it exo or endothermic? What's happening to the bonds? And then you're going to write in your answer right there. Okay, pause the video, do that. Okie dokie. Okay, last example problem we're going to do for this one. This is just a general thermochemical equation and an example problem that you might see show up on any test. So how many kilojoules are given off when 17.8 moles of methane react? We're given some information about the balanced chemical equation and the enthalpy change for the reaction. So first thing we want to think about, enthalpy change is negative 890.1 kilojoules. This tells us the reaction is exothermic. So this means more energy will be released in this reaction. Okay, so if we want to think about the exact amount of energy that gets released here, well, first thing we have to know is that we're working with 17.8 moles of methane. If we look at our chemical equation, how many moles of methane react per this reaction? 1, because our coefficient is 1. So I don't have 1 mole of methane, but what I can use is my enthalpy change, because what we have to remember is that this is kilojoules per mole as our units. So I can use that as a conversion factor. So I'm going to start with 17.8 moles of methane over 1. Now, excuse me, how do I find how many kilojoules are given off? Or really what this is asking is how much energy is given off? Well, I'm going to use my delta H as my conversion factor. I know that for every 1 mole of methane in this reaction, negative 890.1 kilojoules of energy are released. So if I plug this into my calculator, I'm going to get my final answer here in kilojoules, and I'll let you go ahead and do that. So this is just an example of a problem, a classic thermochemistry problem about how you can figure out enthalpy, use enthalpy of reaction to help you figure out heat when any amount of a substance is reacted. Okay? All right, that's your video for this one. Bye.